Hi, my name is Vishnu. I'm a postdoc at Tel Aviv University, and today I'm going to be presenting our work, Fair Division via Quantile shares. This is joint work with my advisor at Tel Aviv, Michal Feldman, and with Yakov Babichenko and Ron Holtzman from Technion. I'll begin with a quick introduction to fair division. So the problem asks, how should a collection of agents divide a set of items amongst themselves in a fair manner? There are, of course, tons of applications for this, like the fair division of estates, borders, airport traffic, etc. But the simplest sort of picture you can draw for this is the following. You have a set of n agents and a collection of m items that they want to share amongst themselves. I have just some office supplies here, and you want to divide these items amongst the agents. So all of the items are assigned, and every agent gets some bundle of these items. And for this talk, we're going to consider allocations that are indivisible, so we don't allow fractional allocations, and deterministic. So we're not going to look at random allocations. Before we can do any of this, of course, this raises the important question of what does it mean for an allocation to be fair? So that's what the fair division problem discusses. And the goal is to try to come up with fairness definitions that mirror our intuitive understanding of fairness. And then you can ask questions like, does there always exist a fair allocation, and can we efficiently compute one? So the fair division literature has two broad approaches to define fairness. They are NV-based fairness and share-based fairness. In NV-based fairness, an agent compares its bundle with the bundles of the other agents. And in share-based fairness, it compares its bundle with some fair share threshold to decide whether the bundle is fair or not. In this talk, we're going to focus on fair shares. So we'll need some preliminaries. In the problem, there are m items. And for now, we'll consider the case where the items are goods. And these are going to be allocated to n agents. Every agent I has a valuation function v sub I, and we make some standard assumptions. And v sub I is normalized, which means vi of the empty set is 0. And vi is monotone, which means if you add some item to your bundle, your value weakly increases. And normally we make some additional assumptions as well in the fair division literature. The most common one being the valuations belong to a class C of set functions. So the valuations have some structure beyond being normalized and monotone. So for example, with additive valuations, the value of a set may be the sum of the singleton values. But for the purposes of our talk, most of what we'll discuss is with no additional assumptions, just normalized and monotone valuations. And here an allocation is an ordered partition of the items. So given an allocation A, A1 through AN, we say that agent I's utility from this allocation is VI of AI, or value for this allocation, because AI is the bundle that agent I gets. So for this quick example that I'm going to use as a running example for this talk, we have two agents, Alice and Bob, and three items, the table, chair, and laptop. And you can think of these as being additive valuations. So the table lists the values that Alice and Bob have for these singleton items, and the value for a set is just the sum of the values for the singleton. For example, Alice's value for the chair and the laptop together would be 550. Okay, so the first category of fairness definitions, like I mentioned, is fairness via comparison. And the standard fairness via comparison notion is envy freeness. So an allocation A is envy free if no one envies anyone else, as the name suggests. So VI of AI is at least VI of AJ for all agents I and J. So when the items are divisible, envy-free allocations always exist under very mild assumptions. This is well known from the cake cutting literature. But of course, when the items are indivisible, an envy-free allocation may not exist. This is very easy to see. For example, one very valuable item. So the example we already had, the laptop has much higher value than the other two items. So however you partition these items between the two agents, the agent that gets the laptop is going to be envied by the other agent. So to remedy this, the literature has come up with a bunch of relaxations of envy freeness, the most prominent of which is EF1, envy free up to one item. EF1 allows for some envy between agents, but that envy is bounded. So an allocation A is EF1 if VI of AI, agent I's value for its own bundle, is at least VI of AJ minus G, I's value for J's bundle, minus some item G. There exists some G in AJ where this is true whenever I envies J. For example, this allocation is EF1. So even though Alice has high value, a value of 500 for Bob's laptop and 150 for Alice's own table and chair, if Bob were to hide the laptop, Alice no longer envies Bob. So the envy from Alice towards Bob is bounded by the one item, the laptop. So this allocation is EF1. And this is not an accident. It turns out that EF1 allocations exist for all profiles of monotone valuations. So with that, let's look at fairness via shares. A share function tau is now a function that assigns some threshold value for each agent, which we call its share. And then we say an allocation is fair towards the agent I if the agent I's value is at least its share value. So Vi of AI is at least tau of Vi comma n, where the share tau is a function of the agent's valuation and also the number of agents that the items are to be partitioned amongst. And of course, an allocation is fair generally if it is fair towards all of the agents. This was formalized in very recent work by Babayoff and Feiger, but this notion has been around for many decades. Note that a share tau of Vi comma n does not depend on Vj for any other agent j, and also it does not depend on the bundles that the other agents receive, unlike with NV freeness. Here, you only care about your own bundle and whether it crosses the threshold. So the main thing you want to study in the fair shares literature is whether a share is feasible, of course. So a share tau is said to be feasible for a class C of valuations if for every profile of valuations in that class, so for every instance where the agent's valuations belong to that class, there is an allocation that gives every agent at least its share. And we say that tau is universally feasible if the class C of valuations is all monotone valuations. So it's feasible for all monotone valuations. So let's look at some shares in the literature. The most famous share in the literature is the proportional share. It was defined by Banach, Nasser, and Steinhaus many decades ago. And it's pretty straightforward. The proportional share of an agent is just that agent's value for all of the items divided by the number of agents. But of course, if you have a very high value item, again, like the laptop, Alice's proportional share in this example is 650 over 2, which is 325. Bob's is 700 over 2, 350. And you cannot satisfy both of their proportional shares at the same time. So no, the proportional share does not always exist. And in fact, no fractional proportional share is feasible. So if you had, for example, 2 agents and just one positively valued item, you cannot give both agents any positive fraction of the proportional share. There is a famous relaxation of the proportional share called the Maximin share, defined by Budish quite recently. So here the agent partitions the items into n bundles, and then an adversary picks a bundle for that agent. And so the agent if the agent were to do this, it would try to maximize the value of the minimum valued bundle. So this value is called the Maximin share. So there is a partition that induces this maximum value of the minimum valued bundle. This partition may be different across agents. So it's not clear whether the Maximin share is feasible. And it turns out that the Maximin share, in fact, is infeasible even for additive valuations. This was shown by Prakacha and Wang about a decade ago. And this led to a lot of work on this problem. It has been shown that many constant fractions of the Maximin share are feasible for many different valuation classes, like additive, submodular, etc. And there's dozens of papers on this. It's an active research area. However, as soon as you go to monotone valuations, again, no constant fraction is feasible for general monotone valuations. You can see this by a simple example where you have 2 agents, 1 and 2, and 4 items A, B, C, D. So if agent 1 has positive value for AC, for BD, and their supersets, and agent 2 has positive value for AB and for CD, they have different Maximin partitions, so it's not possible to satisfy both of them. Even though they both have positive Maximin share, you cannot give both of them a positive value at the same time. And there are many other shares in the literature, like the any-price share, truncated proportional share, and a few others, but these all have the same problem. So for monotone valuations, no constant fraction is feasible. So now this is the state now. We know that there's no non-trivial share, and there is no constant approximation of any such share that is feasible. And this, of course, raises the obvious question of, is there a reasonable notion of a share that is feasible for all monotone valuations? So in this work, we propose such a notion. We call it the quantile share. The definition is extremely straightforward. It all revolves around the one sentence, which is, consider the perspective of an agent who believes that each item should be allocated to every agent independently with probability 1 over n. Equivalently, an allocation is selected uniformly from the n to the m possible allocations. So let xi be the random bundle of agent I in this allocation. You may be able to see where this is going. We're going to compare any deterministic allocation with this standard random allocation to decide whether it is fair. So the quantile share is a parameterized share notion. So for every q in 0, 1, the q quantile share tau sub q is the q quantile of the random variable vi of xi. What does this mean? If you look at how vi of xi is distributed, you take the value for which a q fraction of the values lie on the left, and that's the Q quantile. And in other words, agent I asks, what is the probability that my allocated bundle is valued at least as much as this random bundle Xi? And an allocation is Q fair if this probability is at least Q for all the agents I. And this raises the main question that we're going to study in this work, which is for what values of Q is the Q quantile share feasible? And our results are that for Q more than 1 over E, this constant factor, the Q quantile share is infeasible for monotone valuations, but also for many structured subclasses like unit demand and additive valuations. And for Q at most 1 over 2E, half the above constant, the Q quantile share is feasible for all monotone valuations conditionally. So if this well-known conjecture of Erdős, the rainbow Erdős matching conjecture, is true. And we also give some unconditional positive results for subclasses of valuations. Specifically for Q at most 0.14 over E, the share is feasible for additive valuations. And for the classes of unit demand and matroid rank valuations, we uncover the exact critical value. Q equal to 1 over E is the critical value. So before we show our proof sketches for this, I want to introduce some alternate motivation for the quantile shares notion. So you can think about quantile shares as veto lists. So an allocator who doesn't know the valuations tries to allocate to the following procedure. So every agent submits a veto list of allocations of size at most L. And here fairness is captured by the fact that L is the same for all of the players. And then the allocator produces one allocation that is not in any of the lists, so has not been vetoed by any of the agents. So as a picture, you can think of the old example with Alice and Bob and the 3 items. So you have 8 possible allocations, and suppose each of them is allowed to submit a veto list of size 3. So in the first Alice vetoes these 3 allocations, and Bob vetoes these other 3 allocations. So there are 2 allocations that survive this veto process, and the allocator can produce this allocation, where Alice gets the table and chair, and Bob gets the laptop. And both of them consider this fair for some value of Q, which we'll get to in a minute. So the question we're asking here is, how large can L be such that the allocator's task is always possible? In the absence of any assumptions, the answer appears trivial at first. So if L is at least the number of allocations over N, this is impossible because in the worst case, everyone can submit disjoint veto lists, which cover all of the allocations. And if L is smaller than the number of allocations over N, there's always going to be some allocation that survives. But of course, monotonicity of the agent's valuations is missing in this picture. So we define a monotone consistent list L if whenever Si, S minus I, so whenever some allocation is in this list, then for every Si prime subset of Si, so for every allocation where I get a subset of that bundle, I must also add that allocation to this list. So the list has to be consistent with some monotone valuation. And if we enforce this, the question is now, how large can L be such that the allocator's task is possible for all monotone consistent list reports? So the reformulation of our main result is assuming the rainbow Erdős matching conjecture for all monotone consistent veto lists of size at most number of allocations over 2E, there is an allocation that survives. So let's quickly look at some infeasibility or feasibility of some simple constant quantiles. The feasibility of the 1 over n quantile we've already seen. It's very simple. So every agent eliminates strictly less than a 1 over n fraction. So at least one allocation survives all eliminations. The infeasibility of the 1 over E quantile comes from this simple example. So suppose you have n agents and n minus 1 items, and suppose all the items have strictly positive value. Then in every allocation, some agent gets nothing because there are fewer items than agents. But in the random allocation, the probability that Vi of Xi is 0 is exactly the probability that Xi is empty, which is 1 minus 1 over n to the n minus 1. The probability that every item was given to someone else, which is approximately 1 over E. And so the 1 over E quantile is infeasible. Any quantile larger than 1 over E is infeasible. This immediately gives us this corollary. We've already solved this problem for 2 agents. So Q equal to 1/2 is a critical threshold between feasibility because 1 over n is 1/2. And infeasibility because 1 minus 1 over n to the n minus 1 is also 1/2. But of course, this problem is harder for larger n. And in order to make some progress, we're going to need the Erdős matching conjecture. So here's what the conjecture states. Given a K uniform hypergraph, so a family of K element sets, the matching number is the size of the largest matching, so the largest collection of pairwise disjoint sets in F. In this example, we have the ground set are all of these black dots, and we have a 6 uniform hypergraph. containing these 5 circled sets. And the matching number is the size of the largest matching here, which is 3 in this example. So Erdős asked, how large can a K-uniform hypergraph on M vertices be if it has no n matching? And he conjectured that for every mk and n, where m is at least kn, and for every family that does not have an n matching, so whose matching number is less than n, we have that the size of this family, the number of sets in this family, is at most the maximum of these 2 expressions. What are these expressions? The first one is just the hypergraph containing all k element sets that have at least 1 element out of the first n minus 1 elements. So of course, if every set has 1 element of the first n minus 1, if you pick n of these sets, they're going to intersect somewhere in the first n minus 1 elements. And so there's no n matching. Hypergraph P is all k element subsets of the first kn minus 1 elements. Once again, if you were to have an n matching amongst k element sets, then they have to have collectively at least kn elements. So you cannot construct an n matching with kn minus 1 elements. So these are 2 examples for which it's easy to see that there's no n matching. And the conjecture is that they are the 2 extreme examples for all values of mkn, where m is at least kn. So there is a large amount of literature on the Erdős matching conjecture. It's known to be true for k equal to 2 and 3, for n equal to 2, which is the famous Erdős-Corrado theorem, and for m sufficiently large relative to n and k, which there's a lot of works in this area, but right now the best bound is about m at least 5 over 3 kn, and some other asymptotic cases. So how do we connect the Erdős matching conjecture with quantile shares? Well, the first thing we're going to do is reduce to monotone 0-1 valuations. So observe that the Q quantile share is feasible for all monotone valuations, if and only if it is feasible for all monotone 0-1 valuations. The forward implication is direct. The backward implication, take a given monotone valuation and consider the Q quantile, set everything to the left of that to value 0 and everything to the right to value 1. Now in this new 0-1 valuation, any Q fair allocation has to give all the agents a 1 bundle. So the same allocation has to be Q fair for the original values. So it suffices to consider 0-1 valuations. So we will first use the Erdős matching conjecture to obtain a bound for identical valuations. So how are they connected? You may be able to see this already. The vertices are the items, M. The hypergraph edges are the 1 bundles that we want to assign ideally to all of the agents. And no n matching in the hypergraph is the same as saying there is no partition into 1 bundles. So by identical valuations, I mean all of the agents have the same valuation function, the same 1 bundles. But there's still some difference between the EMC and quantile shares, namely what is K in the quantile shares problem? The Erdős matching conjecture considers K uniform hypergraphs. So what is the K that we have to use? And it turns out that a careful choice of K, where K is floor of m over n minus 1, does the job. So here's how the proof is going to work at high level. The Erdős matching conjecture says if there is no n matching, then there's an upper bound on the number of 1 bundles, which is a lower bound on the number of 0 bundles, which implies that the Q quantile is at 0 and not 1. To see more details, the full proof sketch is that without loss, we can assume that m is sufficiently large and m over n is an integer. We can do this by adding dummy items of value 0 to our instance. And then we let k equal to m over n minus 1. And suppose there is no n matching. And via the Erdős matching conjecture, we can show that a fraction of at most 1 minus 1 over e of the k bundles are 1 bundles. And therefore, a fraction of at least 1 over e are 0 bundles. And then we can apply the Kruskal-Katona theorem, which bounds the size of a shadow of any family. In this case, the family of k element sets that are 1 bundles. And so it says a fraction of at least 1 over e of the k prime subsets for any k prime less than k are 0 bundles. So now in a random allocation, the size of xi is less than its expectation with probability approximately 1/2. And conditioning on this, vi of xi is 0, so you get a 0 bundle with probability at least 1 over e. And in total, the probability of getting a 0 bundle is at least 1 over 2e, combining these 2 things. That's the whole proof sketch. So we can also do this for non-identical valuations, but we're going to need the rainbow version of the Erdős matching conjecture, where you have n different hypergraphs representing the n different valuation functions. And rainbow matching is a selection of vertex disjoint hyperedges, 1 from each hypergraph, representing the 1 bundle you're going to give to each agent. So the rainbow Erdős matching conjecture is, again, if you have no n matching, then at least one of these hypergraphs has some bounded size, the same bound on the number of hyperedges. There's a stronger conjecture than the Erdős matching conjecture, and it's also been proved for many special cases. And the general theorem that we have is if the rainbow version is true, then the 1/2e quantile share is feasible for all profiles of monotone valuations. And the proof follows the same high-level lines. So other than this, we also give some unconditional proofs. First one is for additive valuations. We say that for every EF1 allocation is 0.14 over E fair. And the way to show this is if you consider an EF1 allocation, then for any agent I, there's a set of at most one item from everyone else's bundle, such that if you remove these from the allocation, I is now NV-free. That's the definition of EF1. So the probability that Xi, the random bundle, gets any of these n-1 items is at most 1 over E. And conditioning on Xi not getting any of these, the probability that Vi of Ai is at least Vi of Xi is at least the probability that the random bundle Xi is less than its expected value. Because when you're NV-free, the value that you have is at least the average value of the bundles. So what is the probability that the sum of IID random variables will be below its expectation? And to solve this, we just need to look towards the literature. Specifically, we use this lemma of Ariely et al. From 2020, which says that this probability is at least about 0.14 times 1 minus 1 over n. So combining this with the 1 over E probability that Xi gets no element of Si, we get the result. We also show for unit demand valuations and matroid rank valuations a tight bound. So valuation function is unit demand. If for every set, my value for the set is the maximum value of a singleton. And we solve this problem completely. Again, every EF1 allocation is 1 over E fair. And these are known to exist, of course, EF1 allocations. And for matroid rank valuations, where your valuation is the rank function of some matroid, it's known that the maximum share is in fact feasible. And we show that the maximum share has a quantile of at least 1 over E minus some small factors. So approximately 1 over E. And this is asymptotically tight for matroid rank valuations as well. I'll end with some remarks. So the first thing is, how does this compare with MMS, the quantile share? So given a class of valuation C, the Q quantile share is feasible for identical agents if and only if the quantile of the maximum share with respect to C and N is always at least Q. Because if you have a Q quantile feasible allocation, it also witnesses the maximum share, maximum partition. And Q quantile shares are incomparable with alpha maximum shares. So one may think that we're able to show some conjectured proof that the Q quantile is feasible for monotone valuations, a lot of evidence for it, because the Q quantile share is weaker, but this is not true. There are many instances for which the Q quantile share is stronger than the alpha maximum share for any constant factor alpha. And then it's also known that supermodular valuations capture all of the hardness of this problem. So if the Q quantile share is feasible, then it's feasible for monotone valuations. And then one might also want to consider bads instead of goods, but the problem becomes extremely simple because if a single bad is allocated, then the agent who receives this bad is 1 over n fair, and that is tight. I'll leave you with some open problems. Of course, the first one is to prove some unconditional feasibility of the constant quantile for monotone valuations. One way to do this is to prove the rainbow Irish matching conjecture, but that's a bigger result in itself. But you can also do this by proving that the EMC bound is correct up to a constant factor. And I don't think this has really been studied much. Some other open problems are to prove unconditional feasibility for special cases, improve the additive bound, or prove it for submodular or subadditive. And you could also consider extending the study of quantile shares to random allocations or to arbitrary entitlements. So we tend to conjecture that 1 minus 1 over n to the n minus 1, so 1 over E, is the correct critical threshold. We prove this for unit demand and matroid rank valuations, but also we prove it analytically for small values of n and m, and we prove it by computer solver for some slightly larger values of n and m. And finally, we have this proposition that the 1 over 2e bound is tight if every agent must get approximately the same number of items. And so the Erdős matching conjecture, rainbow Erdős matching conjecture, which consider equal sized bundles that are allocated to the agents, cannot do better than 1 over 2e. So you will need new techniques. You'll need very unbalanced allocations to get to 1 over e. Also, of course, our arguments for monotone valuations are not constructive, and this leaves open many questions about algorithms and hardness results for all of this. And that's the end of my talk.